Great, thanks. Thanks for coming, everyone. Thank you for the invitation and introduction. So today I will talking about product sets of arithmetic progressions. I hope this is accessible to most all the audience, and it's based on very recent joint work with Yunkun Zhou. He's a PhD student at Stanford as well. Okay, so the talk will begin with some motivations. Like I will introduce two fairly famous problem in number theory and additive combinatorics. And then I will mention some main ideas in the proof of our theorems. So we begin by Erdős multiplication table problem. So the problem asking if you take the product set of first n integers, then how large is this product set? So this just means 1 to up to capital N. And the first well-known, of course, you can say that this M is at most something like half n squared because it's the multiplication table is symmetric. And but beyond that, I think the first non-trivial fact is Mn, this size is little o n squared. And it has a very beautiful proof. We quickly go through this. So the proof based on the Hardy-Ramanujan theorem, it says that all but at most little o n number of integers from 1 up to capital N will have log n number of prime factors. Let's say we're counting with the multiplicity to make this proof more rigorous here. And so by applying this theorem, we know that all but at most little o n squared number in the multiplication table will have 2 times log n number of prime factors, because basically any product will look like A times B, and if A, B are both typical, then you should believe that there are like 2 times log n number of prime factors. But we know that typical number from n up to n squared will have log n squared number of prime factors, but log n squared is roughly still log n. So that means our typical elements in the multiplication table will be antitypical from 1 up to n squared. So it's like little o n squared. So that's a simple proof of this fact. It's a beautiful proof, and at least it indicates something. When you want to understand this size of this multiplication table, you probably want to take into some arithmetic information into account, such as studying this number of prime factors functions. So later this talk, so omega n, little omega n will be the number of distinct prime factors, and capital omega n will be counting with multiplicities. And in my talk today, actually these two functions, you can assume they're the same. And whenever which one is more convenient, you just assume which one. Okay. So let me give a quick summary of this problem. So let's delta be this symmetrical constant 1 minus 1 plus log 2 over log 2, which is approximately 0.086. And Erdos in 1960s ruled that Mn is n squared over log n to this magical constant up to little o1 factor in the exponent. And Tannenbaum made this little o1 more precise, and it's up to exp to the power log n to half plus epsilon here. And actually, I think this epsilon can also be made, he can make this very precise, like triple log. I just skip it here. And finally, in 2008, Ford remarkably determined this quantity Mn. So up to a multiplication constant, this quantity is completely determined now. So it's n squared over log n to the delta, and the next order is log n. And the exponent is also determined, it's 3 halves. Okay, that's basically a quick summary of these problems.
Then Erdős and Tannenbaum prove lower bounds, or they're just upper bounds?
let me see. So I believe they prove at least they prove this lower bound, but let's see. I think upper bound is even easier. So
Erdős's result is upper and lower. The Tenenbaum result that is listed here is only a lower bound.
I see.
It should be greater than equal. Yeah.
Okay. Thanks. Okay. Thanks for the comments.
Just a question on the notation on the Ford result. Is that with the constant or is that a theta result?
Theta, sorry.
Okay, that's fine. I didn't know the notation. Thank you.
Okay, sorry. Yeah, this is same as theta notation. Okay, thank you. Then Elekes and Ruzsa in the paper called Few Sum Many Products, they mentioned one problem is if now we consider the parallel question for instead of just first n integers, but any arbitrary arithmetic progression with length n, then what can you say about this size of product set? And the conjecture that this shouldn't be much smaller than the quantity in the multiplication table. Basically, the conjecture that a dot a will be at least has size n squared over log n to the delta plus little 1. So here this quantity again, maybe I should write. This is also means up to a constant. At least. So our first result I mentioned today is that we prove this conjecture is true. And so the strong revision we can do is actually n squared over log n delta and also log n to some power c. But we cannot do something like as Ford did in his paper, like 3/2. I would say it's larger, like something more like 7/2 or something. So we lost some power of log n here. That's basically a statement of the first theorem. Any question and this? If no, I will move on to the second problem I want to mention.
So when you say you can get, or it might be 7/2, does that mean you have an example that goes below Ford's 1/2?
You mean like that? Sorry, no, actually we don't. We just our proof is not probably optimal or something.
Oh, so you're saying your proof might optimize at 7/2?
Yeah. I'm not claiming the phenomena is different from what Ford did. Yeah. Thank you. So yeah, I will comment why I believe we lost some power of log there. So another problem I want to mention is some product conjecture. So Erdos and similarity conjecture that I believe the original conjectures for integers, but people also can generalize this phenomena to over reals and complex numbers. So let A be a finite set. Today we just focus on integers. And then the conjecture is the size of some set and product set, at least one of them is like close to kind of maximum A squared, up to little 1 factor in the exponent. And wow, there's a lot of progress on this problem. So for example, you can easily find all of them, I guess, on Wikipedia. And I just mentioned record now. So whereas I'm aware of the record now, it's still due to Rudniff and Stevens, they prove that the size is 4/3 plus a little bit, like 2/1000 roughly. So the question I'm interested in today is about some extremal cases of some product conjecture. So by saying extremal cases, I mean like if we assume that one of the quantity is small. small means like very close to the theoretical minimum value. For example, if we assume this product set is only a constant times A, then we want to know how large is sum set. In Chang's theorem, she proved that actually you can even get A square up to multiplicative constant. So her proof involves some so-called additive energy and some exponential sum estimates. And in another direction, now if we assume that A plus A is say small, what can we say about the A dot A? This question has been studied before, so in time you can find this paper on her website, I believe. So it's if you assume that sum set is up to a constant times A, and the product set is at least A to the power 2 minus 1. I should also maybe mention here like this implicit constant. Chang also made it very explicit. I just didn't include it here. Okay, let's go back to this this case, very interesting. And so in 2003, Elekes and Ruzsa, they proved that if sum set is small, then the product set is A squared over log A. So now it's going. So now it's we made this little one factor more explicit. So this bound definitely sharp up to a power of log A now. So, but in another very remarkable paper of Solomoshi, and he proved something. I think the title of the paper is called "Bounding Multiplicative Energy by Sum Set." So he proved something like following. So the product of product set and the square of sum set is at least A fourth power over log A. So as a corollary, if we just plug in the size of sum set is small, then you can get A dot A will be at least A square over log A. So Solomoshi results is in general more general, and in particular, he can recover this result of Elekes and Ruzsa. The proof using very, very clever argument of incidence geometry type, but so it should also works for not just for integers and more general. But so, okay, up to now, then all the progress here are all, it's like it has a log A factor. And you might wondering, do we expect better bounds, or if that's already the best we can do? So as long as we assume that A plus A is smaller than constant times A, do we expect that the best we can do is just A squared over log A? Can we like break through this log A factor? And the answer is we can do better. So at least the conjecture of Elekes and Ruzsa in 2003 in the same paper, the conjecture that actually A dot A should be at least A squared of log A to some power. And this constant is 2 log 2 minus 1. And it will be clear why this 2 log 2 minus 1 show up here. But roughly, so this numerical value is like 0.39. Okay. So that's the conjecture. And now I want to so the conjecture is based on actually a special case. In a paper of Pomerance and Sarkozy, they proved in a special case that if you take set A to be a subset of 1 up to n, and set A has a positive density, then they prove that the product set of the product set A dot A will be at least this quantity conjecture as I wrote here. So so Elekes and Ruzsa, and based on the result of Pomerance and Sarkozy, they believe that this should be true for all set A with constant doubling number. Let's say that sum set is very small. Okay, that's conjecture. Now I want to give a heuristic reason why Pomerance and Sarkozy's result is true. And also that's indicated some idea in our later proofs. So let's just consider a simple case. So if A is a subset of N, and we know that the density of A is, let's say just constant density at least, and then how small can A dot A? I hope this the Heuris argument it makes sense and not misleading. So let's just choose A prime to be a subset of A, and we pick up all those typical numbers. Typical numbers, by typical, I just mean like in the sense of Hardy-Ramanujan theorem. So that means we pick up all the n such that omega n is roughly log n. Okay. Then we trivially just bound the A dot A original product set by the product set of this subset. So this is of course always true. And now each product in our new product set A prime dot A prime will be looks like form AB and has approximately omega AB is approximately, let's say, 2 log n. Okay. And now we consider a set of all n up to n square such that omega n is roughly 2 log n. And we might expect, okay, we might expect that this A prime dot A prime is comparable to the number of all integers up to n square such that omega n is around 2 log n. And the reason we might do this, expect such a thing happen is like, because our A prime is also like constant density roughly. So this is also the same as big theta. So it's like, you might expect this, you might expect all the number with omega n is like 2 log n. This quantity should be comparable, not much larger than the created by taking product of A prime and A prime. That's a heuristic guess. That's the statement I make here. And what they did is just make this more rigorous and make it a proof. So any question for this heuristic argument? Okay, if not, then I want to say how y 2 log 2 minus 1 appears here. So there's a classical formula of counting the number of integers up to x, such that the omega function is k. There are many mathematicians made a contribution for this. For example, when your k is fixed, this formula, let's say k equal to 1, you can look at this expression. Actually, it can prove asymptotic. So it's like x over log x. So this is prime number theorem. And for any general fixed k, you can prove by, for example, induction. So I think this is due to Landau. And then for the range we are interested in, k roughly looks like 2 times log x. I think it's due to Selberg, usually called Selberg's formula. And in some other range, this is made by, for example, by Deline. And there are also parallel results for capital omega n. But let's just mention this as little omega n here. So by plugging the formula for k equal to 2 log x, we should get a asymptote formula like this. So it's like, okay, yes, Selberg. Okay, thank you for Demetrius. So I guess, okay, so then, yeah, so then this is 2 log 2 minus 1 appears, because then you can just using the Stirling formula to approximate k factorial and plug in, you will get this 2 log 2 minus 1. Okay, that's heuristic argument for how 2 log 2 minus 1 appears in this special case. Any questions so far? Okay, if not, then we move on to the original question. like if the sum set is small, like if it's constant W number, how about the product set, the general case? So that's a quick summary of what we know about when you have a constant W number. So let's say A plus A is smaller than CA. We know that if C approximately 2, then basically A is an arithmetic progression. And if like C is around 3, we have Freeman 3K minus 4 theorem saying that the structure of A is also like arithmetic progression. But now A is like a subset of arithmetic progression and with constant density, say. And for general, we know that A is a subset of some generalized arithmetic progression by Freeman-Ruzsa theorem. And another result I want to mention here is due to Eberhard, Green, and Manners. So they prove that if you, instead of taking some set, but taking a different set, and if say W number is like 3.99, then you also get a very good structure theorem about A. It's basically A is also like arithmetic progression, dense subset, let's say, constant proportion. So okay, that's all the kind of important structural result as far as I know. So what we can do is that we basically only do the modest situation, but also in terms this is a typical case. So let's say we can do the case if A is a subset of AP and has constant density, and then we can show this conjecture is true. For example, so this is covering the W number, let's say 2, 3, and in the different set because of Eberhard, Green, Manners result, let's say A minus A up to W roughly 4. This is also covered. That we can know A dot A will be at least A squared over log A to this 2 log 2 minus 1. There are some results by, I think, Campos, and of course you can counting how many set A, say in certain measure, like if it has a constant W number and it's not, then you should expect that the subset of AP is a typical case. Nevertheless, this is a case we can deal with, and for general GAP, we definitely have no idea how to do, for example. Yeah, that's the statement of this of the two results. I will cover some proof later. Any questions so far before I move on to proofs? Okay, so I want to first introduce something called multitude energy. I guess probably most audience are familiar with the definition. So we define this for any two sets A and B, subset of integers, let's say, finite set. And then we define the multitude energy between A and B be the quadruple A1, A2, B1, B2, such that A1, B1 equal to A2, B2. So it's counting the number of solutions to these equations. And when A equal to B, that's the case we will study today. We just write EA. Okay. So why is multitude energy? Well, it's strongly connected to the product set, size of product set by Cauchy-Schwarz, let's say. So the first estimate I want to mention that the product set of A and B will be at least A squared, B squared divided by this energy. So if you want to give a lower bound on AB, it's sufficient to just give, say, upper bound, a corresponding upper bound for multitude energy. This is for general AB. So on another side, we also know that the multiplication of the energy of between A and B is bounded by square root the product of energy of A and square root the product of energy of B. So this shows that the theorem I just listed before for A dot A also easily transferred to A dot B. So as long by this the second point I put here. So it's like if you can prove a good upbound for multiplication energy for A and B, then you know a good bound for multiplicative energy for AB, and that gives you a good lower bound for A dot B. So I won't repeat the statement of theorem, but I just want you aware of that. This is similar conclusion true for A dot B. So I just now restate our results. I hopefully, okay, first one is about the multiplication table problem for arithmetic progression. Our result can be restated in the following way. So let A be a finite arithmetic progression. Then we prove that there exists a subset which has size not much different from A, differed by a log A to some power. And this power is delta over 2. So this delta is still the same delta, the magical constant, such that the multiplicative energy is very small. It's up to a constant to its minimum possible value. So, so because we know this guy is always at least say 2 times A prime, so A prime squared. So you just counting diagonal solution, let's say trivial solution, you always at least have 2 times. So basically the strategy we have here is just to find a reasonably large subset, and its multiplicative energy is very small. And now by using the Cauchy-Schwarz I mentioned before in the previous slides, then the product set of A dot A, so this will imply that A prime dot A prime will be at least say, again, A prime square, but A prime is up to a constant same as A, so this will be. And of course we have A dot A trivially bounded by A prime dot A prime. So sorry, so this is A squared times the log A to the square of this factor. So now you have the, let's say minus little 1. Okay, so that's why this theorem 1 primes implies the original statement I said for theorem 1. The second theorem can be restated in the following way. For any subset of arithmetic progression with at least constant density, then we can find a subset A prime of A, such that A prime is also comparable to A in size, and then the multiplicative energy of A prime is not much larger than A squared, but only larger than log A to 2 log 2 minus 1 power. Yeah, so then again by Cauchy-Schwarz, you know, this gives you the original theorem 2. So that's a statement for multiplication. So now from now out, everything is about multiplicative energy. So everything is about counting solution to the n1, n2 equal to n3, n4. So there are many common features in these two theorems, and the theorem 2 is it's easier than theorem 1 prime. So I will just mainly focus on theorem 2 prime, and then hopefully this theorem 2 prime will give you some indication how theorem 1 prime will go. But I will also mention some additional ideas in theorem 1 prime, and if I have time. So let's go through the main ideas in the proof of theorem 2 prime. As indicated in the previous heuristic argument, we try to do the similar thing. Okay, we may want to pick up a set of elements and call it A prime, let's say this subset, to be the set of typical numbers, whatever it means. So typical, I guess just pick up those. So okay, let's say we just want to pick up those numbers roughly has a correct number of prime factors, if this statement makes sense. So then use a formula I put in the previous slides. By then we want to use this if there's a similar formula for that, and to get this 2 log 2 minus 1. That's a naive hope, and of course that's probably the only reason 2 log 2 minus 1 will appear. But this requires us, for example, if we want to do completely parallel argument, this will require to understand the quantity, say, the number of elements in this your arithmetic progression, and with a given number of distinct prime factors. And probably we'll even want to, if ideally want some uniformly from all or less than many arithmetic progression with a given length. But this certainly cannot be done in general. There are some abstractions. For example, what if your P itself contained a very, very short intervals? So short intervals, I really just mean y, the length of this interval is much smaller than x. Then obviously we cannot say much about this function pi kx. Let's say counting the number of elements in your arithmetic progression with k prime factors. And another issue is like, what if your P, okay, now suppose your P is not too bad. P is containing some reasonable interval, not short. But what if your P is very sparse? Like say, P is very sparse, I mean like the ratio P, the size of P divided the size of your interval is very, very small. Then the distribution of, I mean, the quantity you want to understand probably also behave very irregular. And we certainly don't know how to control that. But it turns out these two problems are not problems actually. They can be solved fairly, they can be avoided. We don't really need to understand it. Can be avoided fairly easy by some reduction steps. So we did a bunch of reduction steps in our paper, for example, if you want to do more details. But I just mentioned two of the most important ones. I think just to specifically dealing with the two abstractions I just mentioned in the previous slides. So we will show that we'll use two lemmas to deduce our problem to only consider some good AP. So good, I mean, so let's say AP is A plus ID, the length of AP is L and common difference is D, and starting with point A, let's say. Then the first lemma very heuristically, roughly speaking, we can assume that a starting point is at least A is at least D times L. So that's roughly speaking, our arithmetic progression will be in a dyadic interval. Let's say 2x. So if this is A and A plus D, A plus DL. Roughly speaking, our AP will be inside this short in this dyadic interval. So we are not actually, we don't need to worry about this short interval stuff. That's the first lemma basic thing. And why this is true? Why we can do this? Okay, remember we are estimating multiplicative energy, and for a given arithmetic progression P and subset of it, then subset of it, and we want to show there exists a further subset of our subset A, such that blah blah blah, the multiplicative energy is small. So I give a sketch of proof why we can do this deduction. We basically diagonally decompose our original set A, our original arithmetic progression P, say. So if this is our original arithmetic progression, what we do is like doing diagonal decomposition. And say this is I1, this is I2, this is I3. And this will be P. We have subset P intersect with I1, P intersects with I2. Then by pigeonhole principle, we know that, then first we can show that up to some point, all the rest will, you can ignore them because all the rest will only containing maybe a constant fraction of elements in your arithmetic progression P. So essentially, you only need to consider the previous several intervals. How many intervals here? I guess is like roughly log 1 over delta. And then in this number of sub-intervals, let's say by pigeonhole principle, we know that at least one of them, the density is large enough. So assume delta is a constant, then delta over log 1 with delta is also a constant. So we can just restrict on certain diagonal intervals. So this is a simple step. The second lemma is, I just call it density. So it's dealing with the sparsity I mentioned before. So we roughly assume that AD is also at most L log L. So if AD is bigger than L log L, we will use some fairly elementary way, combinatorial way to counting the number of solutions to the N1, N2 equal to N3, N4. So that roughly speaking, if AD is, so in such a case, we need to deal with AD at most L log L. Then this already gives you something like the size of P divided the size of L is actually not too small. It's roughly like a power of log A, say 1 over power log A. So then actually that's not sparse. Well, at least some number theoretical result tools can already be applied, let's say. So how to do this? The second lemma. Well, this lemma, to make it, I just restate it in a precise form. So let P be a arithmetic progression, and we assume GCD of AD equal to 1. Of course, if it's not a 1, it doesn't change the modular energy. So, but let's just assume it's 1. And for any subset of it, we can show that the modular energy looks like this form. So the first term 2a squared just coming from the trivial solution to the equation, and then we have the second term. And you can see that if the previous if A is AD bigger than L log L, then the second quantity will be very small. It's at most like A squared, constant time A squared. So we don't need to worry about it. So that's why we can deduce to the case AD is at most L log L. How to prove such a statement? Well, we just do some simple parameterization to this equation, N1, N2 equal to N3, N4. Let's say X1 equal to the GCD of N1, N3. And then we have 4 parameters to parameterize this N1, N2, N3, N4 by using X1, X2, Y1, Y2 in a very straightforward way. And then we're just counting the quadruplets X1, X2, X3, X4. So let's just say fix X1. And without loss of generality, we'll say X2 is at least X1. And then the ratio of X1 and X2 is same as the ratio of N4 and N1. But now Ni all line in the arithmetic progression, we know this ratio is A plus DL over A as the upper bound. But also we should remember that it's in arithmetic progression mode with common difference D. So all the parameters X1 and so all the Ni are congruent to each other mod D, and it implies X1 and X2 are congruent to each other, always congruent to each other. So this implies that, so here you have X2 is in the interval, let's say X1 over and times X1 over A plus DL over A, let's say. But now because they are congruent mod D, so you should divide D roughly by the number of elements in this interval. So that gives you roughly X1 L over A. And then for each yi, it's in the interval A over X1 and A plus DL over X1. So to guarantee the off-diagonal solution exists, we must require Y1 and Y2 are different. So this gives a natural upper bound on the parameter X1 is up to L. And the number of choices for yi basically is the total number of integers in this interval. Then by the congruence issue, we need to divide by D. So roughly speaking, the yi has choice L over X1. So we just put all of them together, sum over all xi, sum over all X1, and number of choice over X2, number of choice over Y1 and Y2. And put them together to give you have what you want. Now, so from now on, we can just focus on this nice P. nice P with AP is lying a diagonal interval and the density is fairly good. And as we discussed in the heuristic before, we want to choose A prime to be the set of A such that omega A is up to log X. X is now is A plus DL, say. That'll be our subset of elements in our A such that containing typical numbers. And now we have two things to do. First is we need to show A prime is comparable to the size of A. So it's not necessary to prove it 1 plus below 1, but let's say at least constant proportion. And then second thing we want to do is that the multiple energy is very small, only log A to some power larger than this A squared. Okay, that's the two things we want to do. But now good thing is we are in a nice AP. So actually these two tasks are not that difficult at all. So the first one will be kind of contained in the second one, the proof, I mean. So let's just look at the second one, the multiple energy estimate. So we do the same parameterization. I will not repeat. We have 4 parameters. We are really interested in the following thing. We're summing over all xi, yi's, such that xi, yj is in our arithmetic progression. And we have this condition written in red lines. That is some annoying thing. Otherwise, the sum can be easily computed as a previous lemma. So how to indicate these red lines? Well, we let K to be this quantity, annoying quantity. So log A plus EL. And we use a very classical trick, probably familiar for most audience from analytic number theory background. So we just outbound 1 by lambda to the power K minus omega. So because lambda is bigger than 1 and K minus omega is, let's say, non-negative. So this guy on the right-hand side is always at least 1, say. But why we do this? Well, now our sum, the red line constriction on the summation now move on to the summand. So it's lambda to the K minus omega, summing over this function. But we know that this function is a multiplicative that you can check. So, and then we basically try to understand some average value of a multiplicative function, non-negative multiplicative function actually here. So, and it turns out we have many classical tools you can apply. For example, Shiu's lemma. I will recall what is Shiu's lemma. But then after you apply Shiu's result, we will get a function only in lambda, let's say. And then we just optimize lambda because this upper bound will be true for any lambda bigger than 1. So obviously, now you choose the optimal lambda, and lambda roughly square root 2. Lambda equal to square root 2 is the optimal choice. And this gives you this 2 log 2 minus 1, white appears. So I just quick recall the Shiu's lemma. So I give you a big version first. I try to, if you haven't seen it before, and then I give a rigorous statement for reference. So let Fn be a multiple function, non-negative, let's say, not growing too fast. So if we know how it grows on Fp, then we generally know how it grows on Fn. But let's say it grows not too fast. And then the sum we're interested in is Fn. N is in an interval, and also N is actually in the arithmetic progression. We want to understand the average of Fn. Okay, this is bounded by, if we forget D is small, let's say, it's roughly y over log x, and exp this quantity, FPOP sum. Okay, this bound actually pretty good. For example, you just plug in F is a constant 1, and this is good. Okay, but this cannot be always true. Suppose 2 things. The AP I say here, the summing over the AP here is not too sparse, and the interval is not too short. So this is sparse and short is exactly previous abstraction I meant before. So okay, I hope it's clear what do I mean by sparse and short here. But roughly speaking, as long as it's not too sparse and too short, and this formula will give you some good upbounds. So if you want to know the rigorous statement, that's roughly I put it here if you want to check. Now, I just before I end the theorem, after the theorem 2' proof, I want to mention conjecture. We believe that a similar thing should also hold for H product. So instead of considering just A1 times A2, you can consider A1 times A2 up to AH, let's say. And then if you know that A plus A is a constant up to it's a constant times A, then how about the size of A to the H-fold product? And we believe that if you just do a similar thing, like pick up all the typical integers and plug in, and using the formula I mentioned a couple of times, you should probably get some quantity, and that quantity probably optimal up to say little 1 of log A. But of course, we have no idea how to prove this for general case at least. And there are some progress towards this, but of course, I don't think that any progress like doing better than log A to some this power like this shape. I didn't cite them here, but I see many good results to Chang, and I think Solomon should also do some results on this. Okay, that's all the proof for the first part. I'm not sure. I prepared some slides for theorem 1', but I don't know how long, when I should expect to stop.
You could go for another 5 minutes. Would that be enough?
Okay, good. Let's just quickly go through 5 minutes. So,
okay. So
now we're going to move on to the mention some additional idea in improving theorem 1'. So it has some many common feature with 2'. All the reduction step we mentioned before will also apply to 1'. So from now on, we just assume our AP is also nice. Okay, in the proof of theorem 1'. And so if you are familiar with the multiplication table problem, you know that picking up all the typical number is not enough. Actually, it's not a correct choice. So typical numbers like globally, it has some certain amount of prime factors. And actually, you also need to you also need to pick up A' to has some good local information. So okay, the subset A' actually we will pick up it denoted by NKA. Says globally it has omega n equal to k prime factors, as k is roughly log L over log 4. And locally, we have some gross condition on the j's prime factor. So typically, I think the alpha should be 1, but here the set we choose is not typical numbers. So it's like alpha, we choose log 4. And then this is a set A' we will pick up. And the reason we can do this, of course, heavily rely on the previous reduction steps. Our P9 is a very nice AP, so we don't, most things can be understood fairly well. So again, we have two tasks. One is saying we want to show that NKA is actually kind of large, at least not too smaller than size of A, in the sense that differ by log A to the negative delta over 2. Delta is a magical constant. This is connected to some Smirnov statistics. If you want to know more details, we did some estimation in our appendix, and also inspired by a paper of Kevin Ford. You can find our reference list. But another task is, again, it's just showing the molecular energy is small. So there are two tasks. For the first task, I don't want to mention too much, but I just want to mention one thing is like, for example, in our proof, you need to involve with counting primes in AP. And based on the current unconditional result, you really need to require the moduli are kind of not very large, it's very small. So that's also why a similar reduction like previous we did are necessary, for example. So I want to quickly mention the second task is like estimate the multiple energy of this set. This is also classical if you're familiar with the multiplication table problem. So basically in the proof, previously we end up estimating some average value of a multiple function looks like lambda to k minus omega, this kind of function. But this is only captures the global information, let's say. And now we also want further detect the local information. So if we write omega nt to be the number of distinct prime factor of p of n divides p, sorry, of n, such that go up to t, then we want to indicate this local function as we mentioned before. Omega nt is like log t over log 4. This is same as the lower bound on the control of j's prime factor. So to indicate this two informations, we apply Shiu's lemma to the, let's say now we put two parameters, lambda 1 and lambda 2, because the exponent is both non-negative, so this guy is at least 1. So then the question will not become optimization problem for one parameter, but a kind of optimization problem for two parameters, lambda 1 and lambda 2, and then you optimize them. And yeah, that's it. Then you get what you want. Yeah, I think it's at 5 minutes. Let's stop here.